Perfect. So hello. I think that this is working. If somebody could just confirm, just to make sure that everything is all right. I'm gonna assume it is. So hi, I'm James, and today I'm gonna be talking about an application which I've created, ZPET, and I'm gonna be talking a little bit about iOS application security and some ways which you can jump into it and hopefully make some discoveries. So I will apologize in advance. There's been some technical issues, which has meant I'm on an older version of this presentation, and the connection might drop. I hope it doesn't, but anyway, we'll do our best. So I'm going to start just... Oh, yep. Oh, yes, a disclaimer, yes. Of course. Okay, so yep, so all of this is for educational purposes only. Please don't pick up somebody's phone and try and dump their data volume or something. Just educational purposes, just try not to do anything malicious. Okay, alright, so a little bit just about iOS. So I like to just make three main points, just in case you're not familiar with iOS as a platform. So it has a Unix-like file system structure. So if you've seen any Linux system or Unix system, it has a pretty similar file system structure no matter which system you're looking at, and so iOS is going to be very similar to that. It's based on XNU, which is Apple's, it's XNU derives from Unix itself, so it's going to be very similar to that. So Apple devices, they also implement the Apple developed secure enclave processor, which handles data protection. So it's going to handle it's sort of like a TPM in a sense that it handles encryption keys for different classes, which I'll talk about in a moment, and it also handles biometrics, and this is implemented on iOS devices from the iPhone 5S and above, and also on the MacBooks from 2017 and above. Cool. So and the last important point is consensual root access is not permitted by default. And so what this means is if you own an iOS device, you are not permitted to log in as root or gain full root access to the root file system. That's not permitted unless you have some sort of exploit or jailbreak. So those are really the three main points. Cool. So let's jump in, and I'm going to talk about just some really basic little bit of information about myself. So I'm a student at Northumbria University, studying cybersecurity and computer networks. I've developed a few projects. So I've developed Spider, which is a research automation framework. So it's a variety of pretty much just scripts, to be honest, which I've just developed to help my workflow. For example, searching for databases which could possibly be of interest. And maybe identifying hidden databases, so ones with like malformed extensions and stuff like that. There's a variety of things which take a little bit of time, and if I can automate that, it just saves a little bit of time when processing a device's file system. So I have Oxygen, which is a virtualization automation VM, and so this is pretty much all of the credits go to Aleph Security, so they're the ones who've actually developed the internals to that. So what I've developed is I've developed a front end and a web interface in order to create new VMs, and it will assign an SSH port so that we can just spin up loads and loads of VMs, and then we can sign into those and make a little device farm. So I've also developed ZPET, so there's an open source iOS data extraction toolkit. So it's went through so many iterations. So the first version was written in C, second one was in C++, and then the current one, which is being worked on, is written in Swift, and I'm going to demo that in a little bit. So ZPET is designed to take a locked iOS device, exploited using Checkmate, which is a bug in Apple devices, and so when the device boots, we gain access to a certain set of data, and then ZPET processes that, and we can then hopefully output some interesting information. And finally, I'm an author of iOS Research and Exploration Volume 1. This one was created on pen and paper, and it sort of encompasses a variety of different security concepts, and so it just goes over quite a few areas. I mean, maybe network security, file system monitoring, a variety of pretty much just different perspectives, and how you sort of choose which one you're going to go for, and then how you would make use of that. I'm also interested in iOS and digital forensics. Well, I am interested in that. Other interests include photography and a good bit of Avicii. So, traditional disk encryption. I've added in a slide for this presentation because I felt that it might provide a nice contrast between traditional disk encryption and then how iOS handles it. So, traditionally, you would have something like BitLocker, TrueCrypt, and I've also added archive encryption and Windows EFS because they're interesting ones to talk about. So pretty much with these options here, we're looking at full disk encryption. So BitLocker can encrypt full disks, and so can TrueCrypt. So they'll use a passphrase for either of them, or a USB, which will hold the encryption keys. But then you can also use a passphrase, which is used to derive then the encryption key, which is used to decrypt the data on the disk. So the password is used as a passphrase of some sort in that design. So without the passphrase or without the USB, you will not be able to gain access to that data. For archive encryption, again, generally passphrase based. So password, passphrase used interchangeably. You would need to crack that passcode in order to get into the data. So the keys are not held in plain text on your device. They are actually they do derive from the passphrase. And Windows EFS, again, sort of an interesting one. It's sort of outside of BitLocker and TrueCrypt, but that is an example of per-file, well, sort of per-file encryption, but it's sort of based on your user profile, so those encryption keys can be extracted. So the idea is, pretty much for this slide, is that the disk encryption keys are not stored on the system, but rather actually they're derived from the passphrase in most cases. And so now I'm going to move on to iOS. So iOS devices, really, really interesting systems. So if we have a locked iOS device, in fact, it's probably easier to actually start with an iOS device that's off. So if we have an iOS device that's off or on, the entire disk is encrypted, all of the data on the disk. And so we have this fully encrypted data chip on the device. And so that if we desolder, just say we desolder the NAND or something like that, we're not going to be able to extract any data from this at all. And so that's going to present a little issue for forensic investigators and examiners, in the sense that they sort of have to gain some sort of access through the device itself. And the reason for that is because of the secure enclave processor. So we start our iPhone and it boots up, and what we'll notice is that it will boot to the lock screen, which is quite unlike some other device types. So for example, Android, it would boot into a sort of pre-boot state, or well, pre-full boot state, and it will ask for the passcode before the device fully boots. So that would be an example of where the boot partition, so the disk on an Android would be split into various volumes. So you would have one volume which handles all of the user data and all of the system, and you would also have another sort of partition or volume which is going to load into this small interface where you can enter in your PIN. This is how it's going to work on an Android device. You would enter that PIN. That would be used to then derive the encryption keys to then unlock the main disk, and then the device would boot, which would take a couple of minutes, which is great. However, in iOS, what happens is there's this sort of hybrid encryption structure where the device, you would press the power button and it would fully turn on instead of booting into one of these pre-boot states. And so we can then press the home button and unlock, just like we would if the device is already post-unlock, or post-first unlock anyway. So there's this really like sort of simplistic interface where everything just sort of it just sort of flows. So there's no sort of interruptions at all. So the device just fully boots, you unlock, and you're straight in. And so there's sort of an art to that, and I'm going to go into how this secure enclave processor, to my understanding, works. So it's all going to make sense in just a second. So the iOS boot process, so I'm going to point out 3 different physical hardware elements. So on the right, in the bottom right, we have the iOS device AP. So the AP stands for Application Processor, and it's pretty much the processor which is going to process just operating system data. So that's going to it's basically just a CPU of the device. So it's going to process most things. And inside that, we also have some device identifiers, which are burned on to the system on chip, which are going to be used during the boot process. We also have Zpec on the left. I've sort of made this abstracted sort of graphic where we can see the key management, and we have a couple of classes of data. And then on the right, up at the top, we have the NAND, which is going to hold all of our encrypted data. So we have a device that's off. So we're going to press the power button. The first thing that's going to happen is the device is, well, it's going to be booting. I shouldn't really said it boots to the lock screen. It's just going to be booting. And the initial communication with the secure enclave processor, or SEP, we can use those words interchangeably. So the device is going to communicate with SEP, and it's going to transmit an initialization request. So SEP is going to boot, so it's sort of like its own mini system, and it's got the AP is going to pass the unique device identifier, and a couple of other values too, which are unique to that iOS device, and will be transmitted to SEP in order to allow for the decryption of certain files. So what SEP is going to do is it's going to take in an input, it will then evaluate that input, and then it will decide which data is allowed to be exposed. And so what we're going to do is we're going to then move over to the next step. So using hardware values, SEP authorizes per file decryption at class 1 only. So I'm going to discuss what this BFU state means in a minute, but essentially what this means is while the device is booting, each file on the system has already been marked with a certain file sort of state in a sense. So you could say all of the core system files could be marked as class 1 files. All the media files and all the user's data could be marked as class 2 files. So then what we have is, rather than a system where we have to boot into a partition and enter in our PIN and then everything gets decrypted, we now have this sort of like hybrid structure where even without a passcode, some files on the system can be decrypted. And then, so SEP authorizes the decryption of these non-sensitive files, and it will permit decryption, and then the device can successfully boot. So the idea in this structure is that the encryption keys are never exposed to the AP, so the application processor. So SEP handles everything to do with encryption. So it handles all of it. So our device boots. Was that the internet going? I hope it's okay. So the device will boot, and we will be at our lock screen. So we're now at our lock screen, and our device is ready to be unlocked. So the user is then going to enter in their passcode. So the passcode is then going to be passed to SEP as an input. And using these hardware values and then the provided passcode, SEP will then evaluate the passcode. So it will take that in, it will evaluate it, and then if the passcode is correct, it will then permit decryption of files at both class 1, so which is our core system, and then class 2, which is all of our user media files. So this is essentially what we would call full file system access. So when our device boots and we enter in our correct passcode, the device itself will then have access to all of the data. So the AP has access to everything. That doesn't mean us as a user has access to it, but just means it can all be exposed to the system. So that means we can unlock and start interfacing with our apps and media. So SEP can then authorize decryption of the files in class 2, allowing where iOS itself requests full file system access. And so that's quite an important point. And so there was actually another point which I was going to make, which I may well have forgotten. I'm sure we'll get onto it. Oh yes, that's the one. Yes, so if we enter in our passcode wrong too many times, so what can happen is the SEP processor can then stop taking in inputs. So instead of us being able to take off the NAND and then try and just crack the passcode by constantly chucking passcodes at it. We can't really do that because Zpec sort of acts as like a middleman in a sense for data access. And so all Zpec has to do if a device is disabled is it just stops accepting these requests for passcode entry. And so the user will never be able to unlock their device if the device is disabled, unless again you have some sort of exploit, which is I believe there is one that hasn't been released, but it has been talked about. So a couple of additional points. Again, the NAND cannot be desoldered and read externally, even with a passcode. So you can have the passcode. You can you can know what the passcode is for a device. You can take off the NAND. You can chuck that passcode at it all day. You could try every single possible passcode, but you will not get access to the data because the passcode is not the passphrase, which is then used to decrypt the data. It's passed through another processor, the Zpec processor, and then that will permit decryption using the keys which it holds internally. So another important point, the Zpec cannot be reflashed with a malicious firmware. So Apple uses a process called Tss Authorization. So Apple they use public key authentication in order to sign installation requests. So on the Apple call it on the silicon, the Apple's public key will be written to the device, and that cannot be modified. So whenever a package from Apple is downloaded, so just say like an installer for some firmware updates, Apple will upload, so this is the personalization process, they upload those device-specific IDs which are on your CPU, so they upload those to Apple. Apple will then take this firmware file and they will sign something called a ticket, and they will sign this using their private key, so they sign it, they're the only ones who hold the private key, so they're the only people that can sign it. They sign this ticket which has your device ID inside. It wraps it with the current time and date as well, I believe. So we have the ECID, the time and date, and there's also a custom string which the device generates, which is then sent up to Apple, and then it's all cross-checked, all put together into this authorization ticket, sent back to the device, and then if all is well, then the firmware installs. The private key has not leaked, and I don't think it will. Yeah, that'd be very unlikely. And so we cannot install malicious firmware on the Zpec. As investigators and researchers, I think I've already sort of made this clear to some extent, but our position is not attacking the Zpec. It's to use the hybrid nature of Zpec to our advantage. So we want to extract that data which is marked as non-sensitive. And we'll learn very quickly that some of the data that's marked as non-sensitive is actually very sensitive, so it all depends on a variety of factors. So I'm going to talk a tiny little bit about sandboxing. I should have really saved this slide for later, but that's okay. So when we have a running system in iOS, so I've made this sort of graphic here, and this is how iOS, while the device is booted, can help prevent unauthorized data access. So for example, I make this app called Duffy App 2FA app. So I have this application. I also have Duffy App Calendar. Now, these both of these applications could be signed by the same developer. So when an app is installed on an iOS device, it has to be signed, which again means Apple has verified that the app is authentic to some extent, and they're giving it a seal of approval. And what will happen is when the app boots and it loads, it can then request access to certain parts of the system. So this is how Apple prevents access to the full file system to any application on the device. So if I'm in Duffy App Calendar, I can then communicate using a system API to request access to various elements of user data, for example, user photos, health data, calendar data, or maybe even access to the camera. And also the physical hardware too. There are various requests that can take place, and those apply to that specific application. So if I was to, for example, request access to user photos using Duffy App Calendar, then I would be able to access just purely that data and purely via the system APIs, which means the system sort of handles access to external data rather than the application just granting access to everything. And so this is just part of how iOS prevents access to the entire system to a malicious application. Not so important for what we're doing, but it's just something important to note, I think. And so there's a little problem with Apple's implementation, and especially when it comes to BFU and marking data as non-sensitive. So for people here that own an iPhone, you might have noticed that it's possible for applications to sync with their servers and accounts before the device is unlocked. And so this doesn't mean, I have my phone right here. It doesn't mean that I just pick it up and I would expect it to not sync with my servers. I would. But if I turned my phone off, the entire file system is of course encrypted, and then I turn it on, without entering in a passcode, that synchronization is still occurring with those servers and accounts. And what that means in a sense is that the device is still able to sync. And for the device to be able to sync without the passcode entry, it means that only those files at class 1 are still accessible, which would make sense. But then what it also means is that these sync keys, or whichever data is being used to sync those accounts or pull new emails, what it also means is that data must be held at class 1, or at least the synchronization keys, because the device has access to it. The device will have exactly the same, the device will have access. It doesn't just prevent access to the user, it doesn't have access itself until we enter in that passcode to class 2. So all of these sync keys must be held at class 1. And so the problem with a lot of applications is that they do not take advantage of some Apple provided APIs in order to protect their user data. So the problem really is that if these values are being loaded prior to unlock and then being held on a decrypted form on the device, it means that anybody with any sort of exploit or any sort of boot ROM exploit, which is an example of that would be Checkmate, is of course very unlikely for a boot ROM exploit to come around, but it has, and Apple haven't really made any changes to how their pre-unlock state works, and this exposes a lot of user data. So the benefits really of Apple's hybrid implementation is it's really to do with speed. So if the user turns on their device, they don't have that 2-minute wait after entering in their PIN. They turn on their device, they enter their PIN, and there's this really, really smooth unlock, and everything is all ready to go. It's a bit of a trade-off in some sense. I mean, even if the hybrid implementation was still there, but then the data was held at a class 2, and just the very, very core system was held at class 1, I reckon that would still be very beneficial, both in a speed sense and a security sense. But anyway, they don't do that, and it's great for forensics. So the encryption state, so we've got BFU, which I've been talking about a little bit. So this is before that first unlock, so while the device is locked. We also have AFU, so this is after the first unlock. So I'm going to talk about this from a forensic investigator's perspective. So I'm going to start with BFU. So this is where access to the device passcode is not possible. So in this state, the majority of the user's information and media is still encrypted and completely inaccessible to the examiner. So there's no way that you're going to gain access to that data without access to software from, hardware really, from some providers, or using something like Celebrate Advanced Services, where they will hold some exploits. So the last point really there is that account sync tokens and system caches and logs are often held in a decrypted form, because of course inherently logs have to be built before the device is fully unlocked. But what it also does is it allows access to previous logs sometimes, depending on which ones you're looking at, which can expose some sensitive user information. So let's say we have the AFU, or after first unlock state, which is where the investigator is in possession of the user's passcode. This is really the sort of golden state, if you like, where you can just enter in the passcode and you can really access the user media volume without any limitations, but still you have to pertain to, you have to maintain compliance with Apple's restrictions. So if a device wasn't able to be jailbroken, so you can't access the full file system in some cases, but what you can do is you can install a application which can then request access to all of these different software features. So for example, like your photos and health and all that sort of stuff. So it makes use of those sandboxing sort of consensual escapes in a sense. So limited access to certain data. So some forensic applications will just have this application which allows access to all of it, and it will just collect that data and then transmit it back to the investigator's machine. If a device can be jailbroken, happy days. We can just SSH into the device, so we can establish a communication channel, and we can just directly just grab everything. So those are really the basic encryption states. So I'm going to talk a little bit about ZPET. So I've added in this slide just to really point out what ZPET is really trying to do. So ZPET is not trying to bypass Zpec, and it makes no claim to do so. What it's trying to do is it's really trying to take advantage of the user data, which is held at class 1. So this is before the first unlock, and what we're really trying to do is take advantage of these sort of inherent vulnerabilities that Apple have sort of which they've implemented in some sense, and app developers too. For example, Snapchat exposes all the users' messages, and sometimes visual media too, in the class 1 state, which is a complete misuse of Apple's protection APIs. But what it also means is that Zpec can then pass this, and then we can extract full chat data without the user's passcode. All we need is physical possession of the device, and this is really an issue in my opinion. Well, an issue and a success in terms of forensics, but for user privacy, it's a little bit questionable. We can also grab information on, for example, there's a very, very wide range. We could talk about access to VPN credentials, mostly usernames and just domains, but there have been passcodes as well in some cases. So some applications will save your password in plain text in its local user data access, and we can then extract and then pass that information if it's being held at class 1. So again, a complete misuse of Apple's protection APIs. And if these app developers did implement it properly, so app developers, they could just say, right, we're going to actually make this data only accessible at class 2, and then that would be an extremely effective solution, because we're not going to access that data. We won't be able to. There is no bypass for that. But app developers and Apple, in some cases too, don't do that. So here we are today talking about extracting data. I talked about this a little bit before, but the BFU stay in iOS and Android. So on Android, again, we have this mini OS environment, 1 to 2 minutes to boot, probably less than that now, but when I had an Android anyway, it was around that. So then we have this sort of like security over speed implementation. Of course, there are some exploits on Android devices too, well, there are many actually, which exploit some issues with the built-in TPM, so then extract the keys and then unlock. But if there is a very secure implementation of it, and there are no exploits available, then because I suppose you could say that about any system, then it's good, and it's real full disk encryption. Whereas on the iOS side, so the device will fully boot, and it will limit again the decryption to files at class 1. So we have an instant entry into the OS environment, a couple of seconds, less than that. Speed over security again, but when the device boots, the Zpec will permit decryption of class 1, and it's just important to note that this is only if the boot environment is trusted. So those device-specific keys, which I mentioned earlier, or those device-specific identifiers, those have to match, and for Zpec to accept those and then permit decryption of class 1. So what can we really do as researchers? So I pasted a couple of pictures here, and these pictures are a little bit old, but that's okay. So we have Checkmate, and Checkmate is an exploit which has been released, and that works on the level of the boot ROM. So exploits an issue with the boot ROM which cannot be patched because it's in the hardware, and we are then able to compromise the boot chain, because each element of the boot chain is sort of like incrementally checked as the device boots. So each next element will check its element before and after and itself. It's some abstraction anyway. And because the boot ROM is the first element, we can then compromise that entire chain and then boot the device. So the device boots, those specific device values match. So then what happens is when the device boots, we can then use we can use Checkmate to then boot the device using that exploit. We then send something called a binary pack, which will then send an SSH daemon so that when the device boots, we now have the same access to the device as the device. And so what this means is, due to this exploit, we can then sideload the SSH service or daemon. We can then log into the phone virtually, and then we can access everything the phone can access. So this is where those encryption states of BFU and AFU are very, very critical, because we have access to class 1 only before the first unlock. So we have exactly the same access as the device. So we can then start traversing the file system and then extracting files and all of that sort of stuff. If you did try to extract something which is class 2, you'll get permission denied. Cannot be bypassed, but just important to note. So we can also export the full file system structure. So even though we can't get access to things like iCloud documents, what we can do is we can grab all of the file system structures, then we have all of the file system names, sometimes some metadata too. So we can gain a very sort of wide insight into what this device, how this device has been used, and what its real purpose is. So I'm just going to move forward a little bit. So I'm going to talk about some personal research. So example 1, Apple Mail. So this is some research I did with a good friend of mine, Laurie. And so we were working on Apple Mail. We were trying to understand some of the data which was being exposed by this application. And so we did some experimentation. We spent a little while on that. And what we figured was that in Apple Mail, when we composed or received an email message, you can essentially, what you can do is you can, with the device owner, they could print that email to a network printer, for example. And that's great. That's a good feature. But what happened is that all of the emails are held at class 2, so that's great. Well, in most cases anyway, there is some other information which is exposed, but we'll come back to that later. So when this email was prepared to be printed, what happens internally is that a PDF of that email is generated on the device. And the problem with this, and this is an Apple official and built-in application, is that those generated PDFs are available in the BFU state. So those PDFs which the Apple application generates are held at class 1, which means that those can be freely accessed by any attacker with a device which is vulnerable to Checkmate. And so this is really an issue. And so this is Apple with their own protection APIs that are not implemented properly. So these can be extracted. All of these PDFs containing the from, subject, date, and to, kindly actually including the email address too, and precise timestamp. We can extract the entire email body, all of the images, all of that sort of stuff. And we can extract all of that without a passcode and post reboot. So not great. So the second example is Snapchat, which is a very interesting application in some sense, because it leaves almost all of its application data at class 1, which is really peculiar. And I was very, very interested about this because there's so many hints. Well, at the start it was just hints. It was just sort of, oh, this information is for example, geo filters. If you've used Snapchat before, you can take a picture on Snapchat and then you can scroll across, and then you can see these visual representations of where you are. So it could say Newcastle on this sort of transparent filter. And what happens is all of those filters which are being created are then saved on the device as a local PNG at class 1, which, not too sensitive, but still something. So what happens is that we can then read those geofilters by extracting those geofilters from the device, and then using something like Tesseract to process all of those images and extract the text content. You can see that it's not perfect, and some of the data isn't really relevant. So this picture on the left, we can see 11:43 p.m. Is that relevant or going to help anybody? Probably not. We can also see Wednesday. Is that valuable? Probably not, because we don't know what Wednesday. But Exeter, is that valuable? Sort of, because that's my hometown, and I was there. And we know that I was there because it's present in the geofilters, which are only loaded when you're physically at that location. So that could be a pointer to something. We can also check the timestamps behind those geofilters. We also have some very weird text underneath that, which I don't quite understand, but I think it's probably a misinterpreted geofilter. It's not perfect. Then we have T12 PM, again, not relevant. And Gator said, which is where my accommodation is. So there we are. So we have some geographic information about our user. Perhaps more sensitively, on the right side, we have the sender ID, which I have now. This presentation again is a little bit old, but I've now mapped those to the actual usernames of the friends list, which is on the device. So we can grab full friends lists, and we can see when a message was sent, when it was read, and we can also extract the text content. So this can actually extract the textual contents of our of these conversations, and we can derive some information about that snap. So for example, we can see this the second snap down. We can see where it says catching those HTTP requests. Lol. Cool. Okay. But slightly just below that, all of these formats are all held in something called a Google protobuf. It's developed by Google, and it's just sort of a file format which is completely unformatted, and the developers are the only people who understand how to format that data. So I sort of had to do some weird parsing work to get this to work. But anyway, using that information from those specific cells, which were then extracted from another database, I can probably show you in a minute, we can sort of derive exactly what happened. So for example, in that example, the user was actually replying to another snap. So this part just below, it looks like base 64, I'm not actually sure, but I'm pretty sure it's the ID of the snap that was replied to. So I sent them a snap, they swiped up, and then they typed a reply. So you can sort of see from the message actually that they were replying to something. They were either replying to a private snap or to something on my Snapchat story. And the one just below, we can just see the message reply. So this was just in the chat. It wasn't actually replying to a snap, it was just to the text. So we can just get some sort of rough idea of what's going on. And again, this is all without a passcode. So sort of where do you start? I mean, you know, if you want to try and grab some of this information, you know, it might look all and good seeing all of that, seeing all of the chats and stuff like that. But how are you going to start? You know, how are you going to get there? So there is such a variety of different avenues in order to start discovering data. And now that Corellium, which is a virtualization platform, now that that's available to the public, that's going to be a fantastic resource to the community in order to facilitate application pen testing and extractions. So I think that that's going to be very valuable. I might run some sort of like mini workshops of sorts if that could be of help. I hope it can. And yeah. So I'd say just dig into the file system. I'll show you some stuff in a second to do with some of the work which I've been doing. And so I have actually added in this slide as well. It's sort of more relevant to forensic investigators. But anyway, just so we don't have a passcode and we need a full file system extraction, there are a few providers. I won't really name them, but it's very expensive. So they're going to have private SEP and boot ROM exploits, very likely, which they're then going to be able to use to essentially crack the passcode, which is against all the current public access, if you like. So we're not really going to focus on that, but it is a thing if you're in law enforcement, and there's a lot of money involved. So yeah. So just really concludes that part of the presentation. Checkmate, Checkmate are going to really help you out. So Checkmate is the actual exploit, which is then going to exploit the boot ROM, and then Checkmate is an application that's sort of encompasses the Checkmate exploit itself, but then it sort of actions it so that then you can start interfacing with the device and stuff like that. Most consumers use it for jailbreaking, so they can install something like Cydia, but they can start installing like visual tweaks and stuff like that. But as researchers, we're going to use it for SSH. You know, we're going to SSH in, we're going to grab some data, and hopefully we're going to find something. So open source is awesome. If you can contribute to some open source projects, I would really recommend creating a GitHub account if you haven't already. And you know, maybe there's something you see in like an open source application, especially in forensics. You know, that there's always improvements that can be made all the time. So if you see a repository and you're like, oh, I could add this, add it, create a pull request, and this could be really valuable for the entire community, because we're really working towards one goal of really enhancing the amount of data that's going to be available from these devices. So I have a couple more pictures which I don't really think are very relevant because I'm going to show you in a second anyway. And I'll take questions in a couple of moments. We've only got a couple of minutes, but anyway, I'm going to move back over. Oops. I'm going to minimize this. Now I'm going to open up ZPET. This is a very, very early version, and apparently I'm not activated. Okay. So I'm going to have to quickly grab a key from my device. Sorry about this. A few technical issues prior to the presentation, and I'm using this other laptop, which is causing some issues for me, but that's okay. So I'm gonna scroll down. There we go. I can use this one. Maybe. There we go. Okay.
James, we've just had a question come in on chat.
Oh yeah, of course. Yeah, no worries.
Vulnerable to Checkmate.
Yeah, so it's up to the iPhone X, so up to the iPhone 10, all the way down to well, very, very early. I think it's actually vulnerable from the 4S all the way up to the iPhone 10, whereas finally, well, it actually wasn't even patched in the iPhone 10R and 10S and stuff like that, but it's not exploitable. It is still there, but there's just not that sort of attack service to be able to get to it. But it is pretty much up to the iPhone X. So I'm just gonna quickly just oops. Awesome. Alright. Let's close that and reopen it. Perfect. Alright, okay, so
Another question, is there a possibility to mark some data aspects as class 2?
Sorry, could you repeat that one more time, please? Sorry. Would you be able to just repeat that question, please?
Is there a possibility to mark some data aspects as class 2? Stream delay's gonna kill all that.
Yeah. I'm gonna open up the chat on my phone just so I can see it. Sorry. Let's have a look. I'm just gonna. Sorry. Let me just grab that. We'll get there.
Is there a possibility to mark some data aspects as
Oh,
class 2?
yes. My bad. So, yes. So, as an app developer, yes. As a user, no. So it's down to the own app's implementation and how it's going to access that data. As an app developer, but yes, you can implement things very securely if you wanted to. But a lot of app developers don't for whatever reason. And so that does present some issues. Now I'm gonna see if I can connect to Corellium. I'm not sure if it'll work while I'm on this call. It's gonna be a little bit risky trying it, but we'll see what happens. Okay, so we have a virtual iOS device here, and if you haven't signed up for Corellium already, I would really recommend that you do. It's a fantastic platform, and if you don't own an iOS device, it allows you to essentially remotely connect an iOS device, so a virtual iOS device. You can go here, create a device, and you can choose which device type you would like. You can edit those unique device IDs and stuff like that. And yeah, it's going to help out your research journey a lot because you can just flash applications and stuff like that to it, and you can access the full file system directly. So you have this nice little user interface for that. And so what I'm hoping to do is connect to ZPET over the internet, which is probably not going to work because I don't have my actual research phone here, and it might cause some disruption, and it doesn't have any data on it either, but this would be much easier with a real device here, but so I'm going to open this case, I'm going to click investigate device, and now we're going to hope for the best. It's going to be a little bit slow because we're connecting over the internet. Cool, so it's detected that, and now at this point while it's running, we're now going to connect to the device over SSH. So SSH is it essentially opens like a two-way sort of communication channel with the connected device. So then allows us to start pulling data, really, from the connected device. So we can then start making requests. I mean, without that, we wouldn't really have a communication channel or like any sort of way of establishing a connection with the device. So it looks like it's not going to play very well today. So I'm going to close that. I'm just going to quickly download an older version. All fun and games.
Internet connection is very fast.
It was alright. Yeah, that was okay. That was not bad at all. I really could not make any complaints at all. That was okay. Alright, so looks like we got another installation. I don't know what we're installing, but apparently we're installing something. Okay. Alright. Let's just try that again, I guess. So if we then install the application. No. Okay. Well, that's fine, I guess. Well, I really would have liked to have been able to demo that today, but no, they are not. Always the way, always the way. But I will upload maybe a short demo video to YouTube, and I'll send that around. And so yeah, that should be okay. Yeah, no, sorry about that, but yeah, I hope it was alright. Other than that, but yeah, hopefully we can do that another time, I guess.
Not a problem. We have another question though in chat.
Yeah, absolutely. I'll see if I can actually open the chat up on my side as well. Just look. No, I don't think I can. No, sorry.
Does Class 2 have limited storage? If not, by increasing its trade-off to speed?
So we have one sort of in entire volume. So if I just go to if I make a new, or probably not a new presentation. Okay, all right. Let's do this. Okay, so if we imagine the entire file system is just this part here. So this is just imagine this is a file system. This is everything that's on the disk. All of that is encrypted, but what it means, there isn't a certain amount of space that's dedicated to class 1 or class 2. So each individual, I really don't know how I'm going to pull this off. I probably won't be able to, but pretty much I guess what I'm trying to say is it's all very, very variable. There won't be any the only speed trade-off that there's going to be is a very, 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 very tiny delay if the files are held at the class 2 state when unlocking the device. But yeah, so it's really not worth the trade-off at all. But yeah, I mean, in terms of actually dedicating.
Basically not noticeable to the average user.
Yeah, of course, yeah. So there's really it can it can change this amount of the amount of volume space which is taking up. So there's class 1 and class 2, but it's it's sort of down to what the system needs, and they're not managed as two separate volumes. They're all one volume, and all of the actual access is actually transparent to the application itself. The system will actually handle that data processing and stuff like that, and because it's all native, it's incredibly speedy. Applications are welcome to implement their own encryption as well if it adheres to Apple's application guidelines. For example, they could hold a database which is encrypted using a passcode, which the user then supplies in the app. I guess that could occur, and then that would have a slight speed effect. But yeah, as for Apple's like native access, the entire volume is very, very variable. So it all works as one. Yeah.
What are the common apps other than just Snapchat, for example? Because we always like to give more than one example.
Oh yeah.
Susceptible to this kind of man-in-the-middle ZPET attack.
Yeah. No, that's a fantastic question. So there's a variety of applications. So for example, let me think. So for example, like Twitter, you're gonna get various information pieces of information from the different user applications. The Apple implemented applications, you're gonna find quite a few artifacts from those. For example, Apple Notes. Every now and then, and this is quite uncontrollable, but sometimes the notes database, which actually contains the user's notes, actually becomes available in the BFU state. And at the moment, I'm studying what actually influences that availability. But sometimes that can become available too. We have a variety of information in Apple Photos. So in Apple Photos, if you create a shared photo album, for example, you could grab the direct URLs for those photo albums as an investigator. Those aren't really going to be of much use unless you have the account credentials, but if it's set to public, if the actual address is set to public, which can be done, I guess that the actual images could be extracted there. For Twitter, you can extract profile pictures, stuff like that. The logged in users account IDs. I'm just scrolling through my apps right now, and I'm just trying to think of some other applications where some of this is very, very accessible. There are like too many that I can even really point out, but you can also pull location records too. So iOS, it will sort of build over time. It'll build this database of, it's extremely unreliable, and I think I have a picture of it on ZPET's website actually. So what I'll do is it'll build this sort of mini database, iOS, and it'll randomly chuck records in whenever it has a bit of free time, and it'll chuck in 100 or more requests whenever it has the time, and it will be historically where the device has been, or the cell towers which it's been connected to. So this is going to be a little bit slow. I think my computer is finally giving up with either the internet connection or 3%. That's not good. See what happens. Very, very slow. I'll just check the OBS is still running. Yep, still going. That's good. You can all probably load this faster than me. Right, so if I scroll down, can I just... No, apparently not. Okay, well, let's just give it a moment, and it will hopefully get there in a second. And so essentially what ZPET can do is it can generate like a sort of like heat map view of the location records which are stored on the device. Again, it's not very reliable, and that's why I've sort of created this heat map view rather than actually what's the best way of putting it, instead of actually just plotting all of these points on a map, because there can be hundreds of them near the same area, but it does give you a rough idea of where the user's been. And there are such a wide variety of databases and methods of accessing different information on the device that it would be hard to pinpoint specific apps. I mean, almost all of the apps give away something, almost all of them will give away something. It'll be very, very variable depending on which application you're looking at, but most of them will give away something. So we can see this view here. It's changed a little bit. Oh, still working, I hope. Maybe. Okay. Yeah, it'll be a little bit variable. But yeah, this is just an example of that location view. So you can see the date and time, and you can see actually down here as well, you can see that these seconds are actually extremely close. So it sort of does them all in like sort of bulk. So it will chuck a ton of records in all at the same time.
Yep, that's Discord just reconnecting.
Oh, yep. Okay. Oh, doesn't sound good. Yep. Let me just. Yep. Looks good. So I do have a couple of other pictures of ZPET running. So we can see the research agent here, and this is going to be quite useful in some sense, because what we can do is we can make, for example, using ZPET, we can make a keyword search of data on the device. We can then identify files in the system where that keyword was present. And then ZPET system, what it can do is it can grab applications' unique identifiers. So each app that's installed on the device will be given its own unique application identifier, which is going to be different per iOS device, per application. So it's all going to change all the time. So you're never going to have the same one as somebody else with the same app. Well, you might, but it's just going to be randomly generated. So basically, ID isn't associated with that specific app. So what ZPET can do is, if that keyword matches a file for an application, ZPET is going to go into that application's directory, and it will then read something called a property list or a plist at the top of the root of that application structure, and it will then be able to correlate it with the application's bundle identifier, and then you can work out which application that data corresponds to, which is going to be quite difficult to identify otherwise. And you can also extract data for that specific application. So there are a few other images here, which I'm pretty sure we've roughly already seen. We also have these this automated extraction and parsing here. So this could actually be quite interesting one to show. So here's an example of a ZPET module. So let me grab the let's say the location JSON. So I have all of these location records, which are then passed out to this map. Now, when TextEdit finally decides to open eventually, what we can do is we can actually open up this JSON, which contains the module sort of definitions. It looks like TextEdit is going to take its time today. We can hope for the best. We'll see what happens. It's really not opening, is it? Can I just... Okay, cool. Well, I can do this. I don't know whether it's very clear, but we can see the file of interest. So it's sort of like a hard-coded directory here. I think it's maybe going to open now. We can set the parse type. So, for example, a SQLite database. And then we have the exact SQL query here too. So this is the data that's going to import, and then ZPET is going to pass this. It's going to pass all of these columns independently, and it's then going to store in the cases database. I would have loved to have been able to actually demo this live, but due to all of the lovely technical issues today, that is sadly not going to be possible. But anyway, I hope it's been sort of I hope it's been enjoyable, and I hope that yeah, it's been helpful, and that yeah, you know, if you have any questions or you want to get further into it and jump in, you know, I would really encourage it. There are so many opportunities that are available to researchers now, especially with Checkmate and Checkmate, that it's really well worth investigating, and it's very unsaturated too. I would comment. You know, so if you're thinking about an app, for example, like Snapchat, I mean, I dug into that, and there was just so much information which, as far as I was aware, wasn't previously public. So, you know, with an application as big as Snapchat, I mean, you could take pretty much any other application, you can find something new in there for sure. So you can really make like a sort of contribution to the forensic community.
an hour, and maybe we'll get some people to come and ask you physical questions and stuff like that.
Oh yeah, sure. Yeah, no, perfect. Yeah, no, that's fantastic. Yeah, no, that's perfect. That's great. Yeah, thank you so much for having me.
Incredibly interesting.
Oh, thank you so much for having me today. I really appreciate it.
I feel like my brain's melted and dripped out my ears.
Pull out my hand from the watch like twice or 3 times.
Oh,
Okay, so we're just going to jump over to the other one. So if you just want to mention that to the YouTube chat, because they can't hear us very well, and just say that you'll be sticking around for a little bit.
yep, sure. So we're gonna jump over to the other so we're gonna jump over to the other YouTube link now, and yeah, I'll stick around like the chat for a bit in the for a while in the Cyberclinic Discord, and yeah, I hope you enjoyed. So thanks so much for watching, and yeah.
Is there another link?
Oh, I don't know. Is it on the same link?
No, I don't think. So it was just going to be. We're going to stop the YouTube presentation and not jump over to Discord. Is what I meant to say, but my words got tumbled around.
Perfect. Okay. No, it was me. Okay, we're gonna jump over to Discord. All right. Wonderful. Okay. All right. Thank you so much.